Howdy, friends. Wanted to work two examples for you that'll help with skill check number 19, which might prove a little bit challenging. So I wanted to at least give you some examples to work from. So we're going to work with polar coordinates and rectangular coordinates, converting to and from each of those. So we got two problems to do. The first one is I've got this integral. Well, let's get a thicker line. Integral 0 to 3, integral minus y to y, x minus y plus 1 dx dy. And I want to convert this to polar coordinates. So that means first thing I need to do is sketch the region of interest. And you can notice here, check out this outer one. Remember, that's like our big slices. And we've got dy running from 0 to 3. So we've got on the y-axis, we're definitely going to have horizontal slices running from 0 to 3. So that's going to be our y range. And then meanwhile, for each of those slices, the x range, so you fix a y with the outside integral. The inside integral, we've got x running from negative y to x goes to positive y. Well, x equals negative y is that perfect diagonal. X equals positive y is that diagonal. Oops. And so now I see what my region's going to be. It's this triangle right here. And I have to convert that into polar coordinates. Sorry, I'm yawning here. So let's do the low-hanging fruit part first. I'm going to use direct substitutions with the change of coordinates stuff to rewrite the integrand. So x is equal to r cosine of theta, y is r sine of theta. So those are just going to go right in here. And we know we're going to need an r. And let's hold off on the dr d theta because now when we think about what's going to go on the outside, am I going to sweep with the radius or am I going to sweep with the angular measurement? And you notice here that if we let theta, do it in bright red here, if I let theta start here and then sweep all the way across, but make sure that for each particular theta slice that I have, the radius goes from 0 to that line right there. So every time I've got a new theta, it's going to go from 0 on up to that line. We see that the the R sweep, the R depends upon, or the R range depends upon where we're at theta wise. So I'm going to put dr and then d theta, and I guess I'm going to do it in red. And the theta is going to run from this perfect diagonal y equals x to this other perfect diagonal y equals negative x. And that's a 45 degrees. So that's pi over 4 there. That's 3 pi over 4 on this side. So pi over 4 to 3 pi over 4. And meanwhile, for every theta slice, I run from 0 to the line y equals 3. Now, how do you convert that into polar coordinates? Well, just remember that y, this should have said r up here. Got kind of weird. This y can be replaced with r sine theta. And so I have r sine theta equals 3, which means that r equals 3 over sine theta is that line across the top. That's the equation of that horizontal line y equals 3. So pretty much just wrap that up. We start r at 0, and then we end at 3 over sine of theta. And I don't think we have to evaluate it for this problem, so that's good. So just remember a couple things. Always insert that R, or at least you need that R there. You're going to have to insert it when you do a conversion from rectangular to polar. Now let's see what happens when we go polar to rectangular. Man. So now I'm going to give you a polar integral, 0 to 2 over cosine theta, and then integral from minus pi over 4 to positive pi over 4, r to the fourth d theta dr. So, what are we going to do here? Well, the one thing we need to keep in mind is that if this is a polar integral, I need to borrow an r over here. So the actual integrand of this integral is r cubed. I'm just going to write that again, keeping everything else the same. But then I have r cubed, r d theta dr. So this is the differential, the area element for polar coordinates. And we're going to just pull that to the side. Now we want to sketch our region. So in terms of sketching a region, we're going to see something kind of similar to what we had the last time. Notice that theta runs from minus pi over 4, so minus 45 degrees, all the way up to positive pi over 4. And erstwhile, for every particular theta that I have, I've got r. And honestly, this integral should be, this is actually asked backwards. These two should be reversed because we need to know what theta is to talk about r. So sorry, I grabbed this out of a book, but it was actually kind of written ass backwards. So let's hold on, let's clean this up just a little bit here. Do you see why it's written backwards? Because that outer integral says theta is a limit, but we don't know what theta is. Theta is determined by that d theta term right there. So let's rewrite. Oops, forgot the RDR. And then this is going to become our dx dy when we actually make it to rectangular coordinates. So sketching that region again, theta runs from minus pi over 4 to positive pi over 4. So again, sweeping in this region. For every particular theta, the r runs from 0 to r equals 2 over cosine of theta. You might think, well, what the heck is 2 over cosine theta equals r? Multiply both sides by cosine of theta, and you get r cosine of theta equals 2. And this we recall as x equals 2. So that means the radius runs from 0 to the line x equals 2. And this would be our region of integration right here. So this line is y equals x. This line is y equals minus x. And we're kind of set up now that we understand the region, we can do the rectangular transformation. I'm going to do that up at the top because I'm running out of space here because I wrote so freaking big. So let me clear up the work at the top. Keep everything else around. Okay, so it seems like the easiest way to do the outer slices is with slices along X. I'm going to do this in blue. I'm going to have nice slices. The top and bottom are going to be defined by y equals minus x and y equals positive x for each x coordinate that I choose. So the outer slicing is going to go 0 to 2, and that's going to be dx. Meanwhile, for every particular x value, the y runs from minus x to positive x. See, it's looking a lot like that other integral we had just a few minutes ago. And then we just have to convert the stuff in the middle. Well, r squared is square root x squared plus y squared. So r cubed is um, x squared plus y squared to the 3/2, right? Because r is square root of x squared plus y squared. And so inside here, I'm going to have x squared plus y squared to the 3/2, and then dy right inside there. And I just almost erased everything because I'm not in pen mode anymore. But then this is my final answer. So your problem 19 is a lot like that in both parts, and I hope that you found this helpful. And I'll see you all on Monday. I got to get going to the conference. Take care. Bye.